Hello and welcome to lecture 39 of the course Theory of Computation. This is also the beginning of week 8. In week 7, we saw languages that are decidable, and then we saw one undecidable language, which was the language ATM, which we also refer to as the halting problem, right? So the undecidable language was ATM was given a specific Turing machine M and a string W. So we have to determine whether this Turing machine M accepts the string W, right? And this was shown to be undecidable. And now, with a lot of hard work and with the theory of countable and uncountable numbers, uncountable sets, we were able to show that this language was undecidable. Now the question is, how do we show, are there other undecidable languages? How do we show the undecidability of other languages? So do we have to do all this like from scratch? Like, do we have to prove the undecidability of other languages in a similar way to how we proved the undecidability of ATM, right? So it turns out that we do not have to do the hard work all over again. We do not have to do all of the hard work, because we could use the notion of reductions. So and use the fact that some known language is undecidable. For now, the one known undecidable language is ATM, but soon we will figure out other undecidable languages as well. So for that, the notion of reductions are going to be very useful. So the reduction, in very simple terms, means that you convert one problem into another. So let's say you take a problem A and you are able to convert that into a problem B, right? So whenever you need to solve problem A, so since you have converted into problem B, you can instead just solve problem B, right? So this is a very, very high level idea of what reductions are, right? So just to give an idea, the figure here gives a pictorial depiction of this. So here we have a sigma star in the rectangle in the left side, and A as the small circle over here, right? So instead of a problem, I am calling it like you can consider it as a set, right? So for instance, maybe the question is, does this given string have an odd number of ones, right? So A will be the set of all strings that have an odd number of ones, right? And sigma star is the set of all strings. So now, instead of asking does the given string have an odd number of ones, we can equivalently ask is the given string in A. Similarly, maybe B is the given string a palindrome. So B is a set of all palindromes, right? So now what I mean by a reduction or a conversion is that is just a mapping. So where if the one string that is in A is mapped to one string in B, so and a string in A is mapped to a string in B, a string that is not in A is mapped to a string not in B, right? So that is what I mean by reduction. So it's very simple. So a yes instance in the left side is mapped to a yes instance in the right side, and a no instance in the left side is mapped to a no instance in the right side, right? So by yes instance, I mean something in A or B. By no instance, I mean something not in A or B, right? So we want to map strings in A to strings in B and strings not in A to strings not in B, right? So that is a meaning of a reduction. So now what is the goal of this? So the goal is that now suppose you want to answer the question, right? A given string, let's say W, a given string W, you want to answer whether this is in A, right? So we don't know, we don't have a way of testing whether this is in A. So now we compute the mapping of W. Suppose the mapping of W was easily computable, right? So then we will map W. Let's say for instance that W was not was in A. Okay, so W was in A, and the mapping is computed. So you get some f of W somewhere over here, right? F of W somewhere over here, right? Let me just write it a bit better. f of w somewhere over here, right? So w was in A, and f of w, this is w, and f of w is in B. So now we know how to like given f of w. So now, just for the sake of understanding, I am saying that f of w is in A and f of w is in B, but we do not know this. We do not know whether w is in A. So we map and compute f of w and then check whether f of w is in B. So if w is in A, f of w is indeed in B, and then when we ask where is f of w in B, we will know that it is in B, and that will help us infer that w was in A. If w was not in A, right? If w was outside, right? Suppose w was outside A, then f of w would also, suppose w was here, then f of w would have been somewhere here. So then when we check whether f of w is in B, then we would get the answer no, and that would help us infer that w is also not in A. So now notice both of these are important. We need yes instance to yes instance mapping, that is anything in A should map to anything in B, and anything not in A should map to something not in B, right? Because if the second thing is also important, because suppose w not in A, right, just for the sake of argument, suppose w not in A got mapped to B, right? Suppose such a mapping like the one that I am drawing now, suppose that was there. Now let's say we check like the mapped instance and we get that it is in B, but we cannot infer anything about where it came from, because it could have been a w that is in A and got mapped to B, or it could have been a w that was not in A and got mapped to B, right? So it is important that this kind of mapping is not there. Every w that is not in A should get mapped to something not in B, right? So this kind of thing should not be there, right? So the goal of the reduction process is to make judgments about some string being in A using something that is already known. Like suppose we have a way to check whether a given string is in B, then instead of checking whether the given string is in A, we can convert it to the mapped instance and then check whether the mapped instance is in B, right? So that's the general game plan here, right? So now suppose we can reduce, so now this leads to some statements. So I'll just state it now and we'll see it a bit more formally after the formally defining the reduction, right? So we can say things like this. Suppose, so this notation means that A is reducible to B, okay? And the notation is A less than or equal to with the subscript M, okay? And B is decidable, meaning we can check whether a string is in B or not. Then A is also decidable because we can convert an A instance to a B instance and then use the decidability of B, right? Suppose A is reducible to B and A is undecidable, right? Suppose there is no way to tell whether A or decide A, then this also implies that B is undecidable. This is because if A was undecidable, or sorry, if B was decidable, right? Suppose if B was decidable, then the reduction, if B was decidable, then A reduces to B and B's decidability gives a decidability for A. So B cannot be decidable. So these are the two main inferences that we get, right? So we'll come back to this, right? So now let us formally define what is a reduction, right? So before that we need to define what is a computable function. A computable function is a function from sigma star to sigma star such that it can be computed by a Turing machine. So what do I mean by computed by a Turing machine? So suppose the Turing machine gets W in the input, it is able to compute f of W and it halts. So it writes f of W on the tape and stops. This is what I mean by Turing machine computing a function. So a function is computable if it can be computed by a Turing machine, right? So not everything is computable, like just like not every language is decidable. We say that a language A is mapping reducible. Okay, so far I will be just saying reducible. So the formal word is mapping reducible or many one reducible. Okay, so this is another terminology, many one reducible. Okay, so we say mapping reducible or many one reducible to language B and denoted by this notation A less than or equal to B. If there is a computable function, right, f, so f is a reduction such that for all w we have this relation. So what is this relation? It's same thing that I have been repeating right from the beginning of this lecture. W is in A if and only if f of w is in B, right. So all the strings, so notice that this is if and only if all the strings in A, so both ways, all the strings in A should get mapped to strings in B and all the strings not in A should get mapped to strings not in B, right. So, or in other words, if f of w was in B, then w must necessarily be in A, right. So if f of w was in E, it should not be the case that w was not in A, right. So it is if and only if w in A, if and only if f of w in B. In other words, w not in A also means f of w is not in B. So such a function that satisfies this properties is called the reduction, right. So two things, one is this relation, this correspondence w in A if and only if f of w is in B, and second is that the function f should be computable, right. It cannot be some arbitrary function that exists, right. So these two together make the reduction, right. So some quick points. First is that a reduction from A to B is also a reduction from A complement to B complement. Why is that? Maybe we'll very quickly draw it on the side. So suppose this is sigma star and this is A, this is B. Suppose there is a mapping, right. So everything in A goes to B and everything not in A goes to not in B. Now we can view the same function by, so not in A is A complement and not in B is B complement. This is also, it maps everything in A complement to something in B complement and everything not in A complement to something not in B complement, right. So if something not in A complement, the double negative, not in A complement means it is in A, to something not in B complement means it's in B. So we can view the same function as also a function from as a reduction from A complement to B complement, right. So maybe I'll just write it here. The reduction f from A to B is also a reduction from A complement to B complement, right. So a reduction from A to B is also a function reduction from A complement to B complement. At this point I want to say another thing. A reduction from A to B need not be a reduction from B to A. Okay, maybe I'll just note it down somewhere. Where do I'll have to move some things around. So one thing, a reduction from A to B maybe I'll just rewrite it. Suppose f is a reduction from A to B, then the inverse of f, right, need not be a reduction from B to A. So we may not be able to, so the main reason is that we may not be able to just invert the function, right. Perhaps, so the only thing that we are saying that everything in A should map to something in B, right? Everything in A should map to something in B. Perhaps everything does not go to the all of B. The image of A may be only a subset of B, right? So that is the reason. So there may be, so we cannot invert the function. There may be other elements in W there may be elements of B that are not images of something in A. So F inverse may not be defined for them, right? So F inverse may not be defined. So that is one point. One other thing is that I just want to stress, when we are checking whether something is a reduction, we need to check two things. First is this correspondence W in A if and only if FW is in B, and second is the function F computable, right? The goal is you transform an instance of A into an instance of B and then use the decider for B. So to get a decider for A, we need to first transform the instance of A to an instance of B and then use the decider. Now, if the transformation is not computable, means we don't know how to get this transformation, then it is not really useful to just have the decider of B, right? So it is important that F be computable. Otherwise, we don't have a computable way to get to the B instance, right? So both of these are important. Whenever we are talking about reduction, both of these needs to be checked, right? Examples. So just to give examples, so the first example is we have in fact already seen some examples in the previous week, right? So if you remember, we showed that A NFA is decidable, right? So this is the acceptance problem of an NFA. So given an NFA, we want to, and a string W, the goal was to show or the goal was to check whether this string is the string accepted by the given NFA. So what we did was we recalled that every NFA has an equivalent DFA, and we constructed this equivalent DFA using the equivalence proof, right? And then given NFA n and a string W, we converted the NFA n to an equivalent DFA m, and then we use the ADFA decider, right? So ADFA is the problem of given a DFA m and a string W is a problem of determining whether the DFA m accepts the string W, right? So now, since n and m are equivalent, it is good enough to answer ADFA on MW, right? Because n and m are equivalent. So n accepts W if and only if m accepts W, right? So we could just run the ADFA decider, right? So we need to construct the equivalent DFA and then run the ADFA decider, right? So this is what I am saying. N accepts W if and only if m accepts W, because n and m are equivalent. In other words, NW is in ANFA if and only if MW is in ADFA, right? Because ANFA just is asking whether n accepts W, and similarly ADFA. So NW is in ANFA if and only if MW is in ADFA, right? So and this is what we want, right? This is what we want. So what we want is W is in A if and only if f of W is in B, right? Here our W is instead of W we have NW is in ANFA if and only if MW is in ADFA. So our W is NW and f of W is MW, right? So and also the conversion process was clearly defined, what is a process, etc. So it's computable. So this is an example of something that we have already done, where what we were doing was a reduction. Another example, also something that we have already done, is the reduction from EQ-DFA to EDFA. So EQ-DFA is the problem of given two DFAs. Are these two equivalent? Do they both recognize the same language? EDFA is a problem of given one DFA. asking whether this accepts the empty language or this recognizes the empty language, right? So what we did, if you remember, if you recall, is that given an EQ-DFA instance, right? So EQ-DFA instance is A, B, right? We constructed a DFA C, right? Okay, so maybe I'll just write that we constructed a DFA C such that C accepts this language, right? This language. What is this? This is the symmetric difference of LA and LB. So this accepts all the strings. So maybe I'll just draw it just for the sake of convenience. So this is L of A and this is L of B. So L of C is everything that is in L of A but not in L of B, and everything that is in L of B but not in L of A. So this shaded portion, so this is sigma star. The shaded portion is what L of C should be. So everything that is in A but not in B, and everything that is in B but not in A. So this is called a symmetric difference. Now if the languages LA and LB are the same, then the symmetric difference will be empty, right? So now after constructing this language, the DFA-C, we can just ask whether, so we have to determine whether A and B are equivalent. So instead what we will do is we will construct this DFA-C which recognizes a symmetric difference, and then just ask whether this DFA, does it accept the empty language, right? So again, once again, L of A equal to L of B if and only if the language of C is empty. In other words, A and B is a yes instance for EQ-DFA if and only if C is a yes instance for EDFA. So all of this, so notice the if and only if. So if this is a yes instance of EQ-DFA, this is a yes instance, and if this is a no instance of EQ-DFA, this is a no instance as well. So this is if and only if, and this is important. It is not enough if one direction is satisfied. For a reduction, we want both of these arrows, right? Both of these should be checked, right? It is not enough if W in A implies F of W in B. Both directions have to be checked. So now, and also the conversion process or the construction process of C is, well, it's a procedural process. You may recall from the closure properties of DFAs that we constructed. Hence, we can construct a DFA C such that this is satisfied, and hence we can say that EQ-DFA reduces to, or mapping reducible to EDFA, right? And hence, since we have a if you remember, we had a decidability process for a decidability algorithm for EDFA. You can use this to decide whether EQ-DFA whether the given EQ-DFA instance is decidable, right? So here in the first case we used ADFA to decide ANFA. Here we are using EDFA's decider to decide EQ-DFA. Okay. So now let us see a slightly different example. So the example is different because so far we were saying that A reduces to B, you can convert A instance to a B instance and then solve B instance, and this helps us solve A instance. So B decidable implies A is decidable, right? So we reduce EQ-DFA to EDFA, EDFA is decidable, hence EQ-DFA is decidable. Now we are going to say the opposite. We are converting A to B. We know that A is not decidable. This implies that B is also not decidable, because if B were decidable, then we could decide A by converting it to B and then solving B, right? But we know that A is not decidable. So this route should not be available to us. We should not be able to convert A to B and then decide B, right? So we know the conversion process exists, so hence B should not be decidable, right? That's the only possible conclusion that we can arrive at, right? So this is such an example. So we will reduce all CFG to EQ-CFG. So what is all CFG? All CFG is a language that consists of description of context-free grammars which accept all the strings or which generate all the strings. So L of G must be sigma star. So all the strings should be generated, right? So it seems like a very easy thing to check. The grammar should generate all possible strings. right? EQ-CFG is the same as EQ-DFA or similar to EQ-DFA. Given two grammars G1 and G2, we are asking whether they both generate the same language, L of G1 equal to L of G2, right? So now we will see how to reduce ALL-CFG to EQ-CFG, right? So ALL-CFG is asking whether this grammar generates everything. EQ-CFG is giving two grammars and asking whether these two grammars are equivalent, right? So this is not that difficult actually. So given a grammar G and as an ALL-CFG instance, right, what we want to know whether G generates everything, right? So it's very easy to convert it into an EQ-CFG instance. What we'll do is we'll construct a CFG H. Okay, it's a very simple CFG. So H is this. H has only two types of rules. The starting one is that the starting variable, just 1 second. So H is this. One is that there is only one variable, which is the starting variable S. S generates AS, where A for any terminal A, and 2 is S generates empty string. So basically any string in the using this sigma, the alphabet sigma can be produced using this. So this is very easy to see. So maybe I'll just note it here. Note L of H is sigma star. Okay. So L of H is sigma star, and so now we can just ask, is G and H equivalent? Instead of asking does G generate everything, we have constructed a grammar that generates everything, and H is, the fact that H generates everything is very easy to see, right? So now instead of asking whether G generates everything, we can ask whether G and H are equivalent, because if G and H are equivalent, G will also generate everything, right? So that's it. So so G is in ALL-CFG, meaning G generates everything, if and only if G generates everything. But then everything, the sigma star is also the language of H. So now it's the same as asking, is G and H equivalent, or are G and H equivalent, right? So G is in ALL-CFG if and only if GH, the pair GH is in EQ-CFG, right? And that's what we want. And the construction of this EQ-CFG instance is also easy, right? All we need to do is, so you are given G, some grammar G, all we need to do is to construct H, and H is this, we just write down this grammar and then give it to the next machine, that's it. So constructing GH is easy, and this if and only if condition is also satisfied. Hence we can say that ALL-CFG reduces to EQ-CFG, right? So this will tells us that ALL-CFG is mapping reducible to EQ-CFG. We can convert an ALL-CFG instance to an EQ-CFG instance. Now suppose I am telling now that ALL-CFG is undecidable, meaning there is no way to decide given a grammar whether it generates all the strings. Now the point that I want to make is that this implies that EQ-CFG is also undecidable. Why? Because if EQ-CFG was decidable, we can decide ALL-CFG by converting it into EQ-CFG and then deciding EQ-CFG, right? If EQ-CFG was decidable, we could do this, but EQ-CFG, but we know that ALL-CFG is not decidable, hence EQ-CFG should not be decidable, otherwise we could do this thing that I said, right? Hence it follows that, so just reading through this again, if EQ-CFG was decidable, we can reduce the ALL-CFG instance to EQ-CFG and then use the EQ-CFG decider to decide ALL-CFG. But then ALL-CFG is undecidable, right? So I'm just stating, I'm just using this without proof. So ALL-CFG is undecidable. So this contradicts that. That implies that our assumption that EQ-CFG was decidable was wrong, hence it is undecidable, right? So ALL-CFG undecidable implies that EQ-CFG is undecidable. So now we have seen decidability and undecidability using reductions. Now let me just formally state it. If A reduces to B and B is decidable, then A is decidable, right? So I'm just formally stating it, this theorem 5.22 in the book. So what do? We first compute, given a string w and we want to check whether it is an A or not, we just compute the function f, which is a reduction from A to B, right. So this is a reduction machine from A to B, and then input f to the decider for B, right. So the assumption is that B is decidable, so there is a decider for B, and whatever, if B says f of w is in B, yes, then we say w is in A. If B says f of w is not in B, then w is not in A. So the black thing is the decider for A. So using a decider for B and the reduction function, we get a decider for A. And the same thing implies that if A reduces to B and A is undecidable, then B is undecidable, right. So this is exactly what we said here in the context of EQ-CFG and ALL-CFG. If B was decidable, by this construction over here, we can construct a decider for A. But if we know A is undecidable, then we cannot have a decider, right. And the next two things are theorem 5.28 and corollary 5.29. It's the same thing, except that we have replaced decidability by recognizability, right. That's the only thing. If A reduces to B and B is Turing recognizable, then A is Turing recognizable, and if A reduces to B and A is not recognizable, then B is also not recognizable. Right. So that's pretty much it for as far as this lecture 39 is concerned. So we saw reductions, and what are reductions? Reductions is a way to transform one problem into one language into another. So main thing is that the reduction should be computable. The function should be computable. There should be a Turing machine that computes this function. And the main thing is that all the yes instances of A should go to yes instances of B, and all the no instances of A should go to the no instances of B. This is the most important thing. Two things to check. One is that the function is computable. Two is that this equivalence, that is, or this correspondence. If W is in A, then f of W is in B. If W is not in A, then f of W is not in B. And if A reduces to B and B is decidable, this implies A is decidable. If A reduces to B and A is undecidable, this implies B is undecidable. So using this, we saw that assuming ALL-CFG was undecidable, we saw that EQ-CFG was undecidable, and we recalled two decidability proofs that we have already seen, and in fact we had used reductions there, but at that time we didn't have the framework for reductions. Now we are kind of setting it in the framework for reductions and viewing them as reductions, right? The ANFA and EQ-DFA proofs. So that completes lecture 39. So now we know how to prove something is undecidable using reductions. So in lecture 40, we'll start proving that certain languages are undecidable by using this corollary 5.23. The corollary that A reduces to B and A is undecidable implies B is undecidable. So that is in lecture 40, and that's all from me in lecture 39. Thank you.